on this computer. Is it not working?
Oh, it is.
There. Okay. We're gonna make it where we can find the exact area under the curve now. We're gonna look at a couple of techniques of doing this. The first technique was what the video focused on, and then the second technique the video didn't go into, so that's what I want to focus on as well at the end today. So this is our way of finding the exact area under any curve, and that's called the definite interval. Now, the technique that the video talked about only lets us do the exact area if we can make geometric shapes from the curves. And so this only works if we can have circles or straight lines. And then we're going to find the area under the curve. Now, if the area in integrals in calculus always happens to deal with this x-axis. And we're talking about the area under the curve to the x-axis. If area is above the x-axis, like it is here and here, it will be a positive value. If the area is under the x-axis, like it is here, we give that a negative value. So the positive area tells us that it's above the x-axis. The negative area tells us it's below the the x-axis. So that's one first thing we're going to look at that you need to be conscious of as you're working through this. Now I'm going to do a couple of problems. Well, we're going to do a couple of problems together. Okay, and it's kind of getting familiar with this new notation here of integrals. So first thing I want to do is I want to find the integral from -6 to -2 of f of x dx. Okay. Now, what this means, this integral from -6 to -2 of f of x dx says find the area under the curve from x equals -6 to x equals -2. So in this case, from x equals -6 to x equals -2, we're trying to find this piece of area. So what geometric shape do I have there?
Semicircle.
A semicircle. What's the formula to find the area of a semicircle? Pi r squared divided by 2. So you half of a circle. What's our radius here? 2. Because I know my diameter is 4, so that means the radius has to be half of that, which is 2. And what will that simplify down to?
6.2.
In terms of pi.
2 pi.
4 pi over 2, which simplifies down to 2 pi. Is that positive area or negative area?
Positive.
Positive. So that's my answer. I figured out my first integral, and that is the exact area under that curve. No overestimate, no underestimate. It is the exact area, which is 2 pi. All right, you try this one. Can you figure out the integral from -2 to 4 of f of x dx? I guess I should mark on this. This is the graph of f of x. Okay, how'd you get that?
6, also between -2 and 4 and 6 units. And it's
Uh-huh.
down 4, so 6 times 4 divided by 2 and negative.
Oh, so you're using the area of a triangle, which is 1/2 base times height. And we know our base is that distance across here, so that's 6. And our height is how far it is, which is 4. And then 1/2 of 6 is 3, 3 times 4 is 12, but you said -12. How'd you get negative?
Under the x-axis.
It's under the x-axis, so this area is gonna be a -12 area.
You can look at the -4 if you really want to put it in one specific place.
Yes.
The value this is positive.
Yeah, technically height is always positive value, but if you want to think about that, like, you could have said, oh, the height is down 4, so you could have put a -4 there. And that's where you can get the negative if you wanted to. Yes, you could do it like that. Think through it like that. Okay. What about, a little bit smaller. What about the, because I can fit it in, the integral from 4 to 18?
42.
Okay, how'd you get that?
The base is 14, the height is 6, and do the area of the triangle.
So base was 14, because 18 minus 4, and height was what?
6.
It is 6. Very good. So that's just 7 times 6, which is
42.
42.
Times 2.
uh-huh,
Okay.
which is
42.
42.
And we're going to operate.
So we end up with 42 there. All right, what would be the integral from -6 to 4 f of x dx?
2 times 12.
Ah, so we can do those properties. Remember when they started talking about the properties of the video, the properties of integrals? And that one property says if I can break this up and say I can figure out the integral from -6 to 2, because that's that nice pretty half circle of my function. And then I can add the integral from 2 to 4, which is a triangle. I can break it up by the shapes. And that is the same as the original. Now the key with this to know that you can break it up, you broke it up correctly, is notice that the upper bound of this integral is equal to the lower bound of this integral.
-2.
And then, sorry. Yeah, it should be -2, thank you. Forgot my negative sign. Is equal to that negative, that lower bound there. And then what's left over, if I put those together, should be equal to our original. And we can get that out. So I've talked about something. So this right here is called the upper bound of the integral. And this number here is called the lower bound.
So is this the calculus part of
Starting, this is the properties. So we'll start to use some of the properties that they talked about. And so we already figured out all of those. That's easy. We already figured out this half circle was 2 pi. And we figured out that green triangle was -12. So our answer is 2 pi minus 12. That's our simplified answer. Okay with that? All right, go to Canvas and do problems 1 through 5, and then we'll do the next type of situation. So this is graphical using geometric areas. I need that area.
How much work do we have to show? Because like for most of these, you could.
This, I do want to see you doing, notice I did my formulas, my area formula and showed that. I want you to see which geometric equation if you're using the area, substituting that formula and getting it. If you have one that has multiple pieces, do show the breakup like I did here. That's the kind of, so yeah. I know you can do a lot of these in your head, but I do kind of want to see which formulas you're using. Huh? No, you don't have to draw the graph. You can just use the graph as that. You don't have to draw the graph. On your board. Okay, so let's talk about the next type of problem. Now, in this case, we're not going to be given the graph, but we still don't know the function. Is that when we were given the graph of the equation, the function, but we didn't know the actual equation. So in this case, we don't know the equation and we don't know the graph, but we know certain information about our function. In order to do these types, we're going to have to use our properties of integrals that was introduced to us. Okay, and they went over them very quickly on the video. For all these properties, we're going to be, I'll write these down. A is always going to be less than C, which is always less than B. And there's notation I'll be using in the intervals I'm talking about. All right, so if I want to find the integral from A to A of some function, what is that always, what's that area always equal to? 0, because I've started at A and moved and went and left at A or stopped at A. So I haven't moved anywhere. So I have 0 area. So that's a good identity to know. Now, if I went from b to a of f of x dx. And so b is actually greater than a. And we can't do that. The lower bound always has to be the smallest number. So we can't evaluate it as that's written. How did she talk about fixing that? Negate it. So we have to set this up as negative, the integral from a to b. The lower bound should always be the smaller number. So we have to fix it if it's not. And that's how you fix it. So that was our next properties. Right? Another one that she talked about is if I have the integral from a to b of f of x dx, and I need to break it up for some reason, I can break this up as the integral from a to c of f of x dx. That's what we did in that last example on the last page, plus the integral from c to b of f of x dx. Again, the key with this one is that the upper bound here has to equal the lower bound here, and the outside, the lower bound here, and the upper bound here has to equal our original upper and lower bound. And then that we can do that. Okay. Then let's see what's the next. Oh, the addition property and subtraction property. So the next one she talked about was we could have a of b of f of x plus or minus e of x. So we can add two functions together. And how we can do that is we can integrate from the area under the curve from a to b of the first function, plus or minus, depending on which operation we're doing, of the area under the curve from a to b of the second equation. So we can break it up like that if we need to. And the one that's used quite often is the constant multiple one. So if I go for integral from a to b of some constant times my function, I can take that constant out, just have that constant times by the interval area under the curve from a to b of my function. I can break it up like that. So those were the properties that were introduced, which you need to know and know how to work with. You have to memorize these. And working with any type of definite interval. This one?
What about it?
What about it?
Yeah. How would
How would what?
force match up?
Oh, that just means that if I'm going to break this up, I can pick some number in between, which I chose as C, and I do the end. I can go. So I'm going from A to C on my x-axis, and then I'm breaking up. Now I'm going from C to B. So A to C plus C to B.
Okay. So
Yeah, we did. Yeah, we did that here, and we did this integral here. We broke it up to this plus this. That's what I did here. So I did that property here. Other questions?
So if we have something that's like 0 to 4 and 0 to 9, and it's going to know from 4 to 9,
You're getting kind of ahead of me. Well, I'm about to do something. So wait till after. If you still have a question after I do this next set of examples, I'm thinking I might answer it. Okay, so here's how this will usually show up in textbooks and stuff that you're working with. Let's say I'm given the integral from 1 to 9 of f of x dx. We know that area is -1. And we know the integral from 7 to 9 of f of x dx is equal to 5. And I know the integral from 7 to 9 of h of x dx is equal to 4. So that's all I know about f of x and h of x. And then you'll be asked to find some certain values. So let's say if I'm asked to find the integral from 1 to 9 of -2 f of x dx. So how can I do that? Okay, first off, I have to, before I can substitute in that -1, I have to get it exactly like this. So I can use my property where I can factor out my constant, and that becomes my constant times 1 to the 9 of f of x dx. And that happens to be information that was given to me. So I can substitute in, I know that integral is -1. And so I take that -1 times the constant -2, and I get an answer of 2. So that's how you would like use the properties and something like that. So that was the constant multiplier. How about, I want to find the integral from 7 to 9 of f of x plus h of x. How would I set that up to do? So I gotta take the integral from 7 to 9 of my f of x function and add that to the integral from 7 to 9 of my g of x function. And do we know those values? Okay, so what's the integral from 7 to 9 of f of x? 5 plus 4. So our answer is 9. All right. I'm gonna have you work these two. All right, see if you can figure out. And this is the one probably gonna answer your question. The integral from 1 to 7 of f of x dx. And then colors. Try the integral from 7 to 9 of 2 f of x minus 3 h of x dx. And the last one over here, the integral from 7 to 7 of h of x dx. Try those three. Yeah. Usually I hard at the end, actually. But it's at the end. Okay, so this one I want to figure out 1 to 7, but I got a problem. For f of x. All I was given was 1 to 9 and 7 to 9 on that. So what I need to do is think of an equation I can work with. Well, if I take the integral from 1 to 7 of f of x dx, and I add the integral from 7 to 9 of f of x dx, that would equal the integral from 1 to 9 of f of x dx. Agree with that? So that'll give me a setup of an equation. Now in this equation, this I don't know. This is my unknown. 7. But I know that the integral from 7 to 9 f of x dx, we know that is 5. And we know the integral from 1 to 9 of f of x dx was given to us as -1. So I can plug in that information. And then I can just solve that equation for the unknown by subtracting 5 from each side. So therefore, I can come up that the integral from 1 to 7 of f of x dx is equal to -6. Taking that -1 minus a 5. So I'm just solving the equation. So I did have to set it up and then plug in my given information and solve for the interval I don't know using just normal algebra skills.
Can we also solve it doing like the integral from 1 to 9 minus the integral from 7 to 9?
Integral from 1 to 9 minus the integral from 7 to 9. You would need to write that as the integral from 1 to 9 plus the integral of 9 to 7. And then realize that you do have to subtract, so you have to negate that. Because we have to set it up so that this upper limit is equal to this lower limit. if I was using that properties.
So
I would
if
have
you
to
like
set it up that way.
skip the first part, it's gonna be wrong.
Huh?
So if you like skip the first sentence, because like,
Yeah, I need to see that work of how, because these are focusing on the properties. So actually, I know a lot, I'm using numbers that you can do kind of in your head, but I want you to focus on the properties that you're using is the key on these. All right, so let's see how we can fix this one. So what properties do I need to work on for D?
constant.
I can bring the constant out. So that's, it doesn't like me to move it at all. Come on. There it goes. Okay, so I can bring the constant out. And that's 7 to 9 of f of x. And then I can also do my subtraction rule. And I can make this minus. And bring that next constant out and distribute my intervals. And we can do it like this. And therefore, I can substitute in, because I was given those values. The interval from 7 to 9 of f of x dx, we know it is 5. And the integral from 7 to 9 of h of x, we know is 4. So that's just 10 minus 12, which is -2. So that's using those properties there. And E is actually one of the easiest ones. What is the integral from 7 to 7 of h of x dx? 0. There you go. Do the next two problems, 6 and 7. Right there. Or the next two problems. Okay, so before I talk about how to find definite integrals when all you're given is the equation, I want to review again how to do indefinite intervals, because we're going to need to be able to do this. So I want to make sure that we can remember how to find the indefinite integral. So that would look something like this. The integral of 3x squared plus 2x minus 26 dx. So what was another word for the indefinite integral? The antiderivative. Remember that? So what we're going to do is this is just having us find the antiderivatives. So notice that the indefinite integral doesn't have numbers. They don't have an upper bound and a lower bound. That's how you determine the difference. And so your answer is going to be an equation. So what is the antiderivative of 3x squared? That is x cubed. Because it becomes 3x cubed over 3, and the 3's cancel out. Plus because that becomes 2x squared over 2, and the 2's cancel out. Minus 26x. Am I done? Plus c. Don't forget the plus c. Always remember your plus c. That's it. So that's our antiderivative that we talked about. Now, what if I needed to figure out, just kind of reviewing this, 6 divided by x to the 4th dx? How would I do that? Very good. And then we can use the power rule that we did before. So what would that be?
Third.
X to the -3rd, because -4 plus 1 is -3. And then so I have that 6, and I'm dividing by that -3. What does that simplify down to?
-2 over x third.
So that is equal to -2 x to the -3 plus c, and then the original problem didn't have negative exponent. So I get rid of my negative exponent. And there's going to be my final answer. So we're okay with that? So that was this one. Now, what if I gave you the integral of 12 over x dx. How would I find that antiderivative?
12 times x to the negative 1.
Okay, so let's say, so you're gonna do 12x to the negative 1 dx.
Twelve.
12 times x to
Negative,
0.
0.
0 over 0. What the heck is that?
Oh,
So,
It's supposed to be 1, like the nature log.
so this one does not, you cannot use the power rule. So if you ever get that x is 0 over 0, if you ever get that over 0, then you realize you cannot do the power rule. Yes, we have to go back to one of our, so you gotta think about what function, when we found the derivative of it, it was equal to 1 over x. Natural log. So this is where I'm gonna do I'm gonna factor out that 12. And it looks like this. So I'm using that property, that constant property I said we use quite a bit. And I know the integral for 1 over x dx is the natural log of x. But remember, x has to be inside, the x has to be positive, right? So how we fix this in integration is we just put that x inside an absolute value. And that fixes it for us. So we don't have to add that other qualifier that we did with the derivative. So I have that's 12 is equal to natural log of the absolute value of x plus c. Let's do a trig one. The integral of negative 2 cosecant x cotangent x dx. Just reviewing some of these rules that I had you needed to start learning in our first video of this section before the Riemann zone. Hopefully you've been studying those. Get in here and start studying them. Okay, so what function, when I took the derivative, I got cosecant cotangent. Negative cosecant, okay? So again, I'm going to factor out that negative 2. And then I have the integral of cosecant x cotangent x dx, which is equal to negative cosecant squared x. And so my final answer is 2 cosecant squared of x plus c, because I need to always remember my c.
Is it cosecant squared x or just cosecant x?
Oh, cosecant, whatever it's squared. It is just cosecant. You're correct. Thank you. Okay. All right, so the next few problems is 8 through 12 is just a review of this antiderivative. So I just want to make sure we have that fresh in our heads before we go through the definite intervals. The last section.
I didn't notice that the 2 in it, 7. I didn't know
Oh, yeah,
luckily D.
Oh, so you figured it out.
That's what you did. U or D.
Okay, all right, that's fine. Yeah, and then you just figured it out. Need a copy again. Okay, so we're going to learn about the definite integral. The definite integral actually is part of what's called the fundamental theorem of calculus. And that's what next class we're going to talk about is the fundamental theorem of calculus part 1 in tonight's puzzle video. And we're also going to talk about the average value theorem. Okay, so the fundamental theorem of calculus part 1 and average value theorem we'll talk about next class. So I want to go ahead and start introducing the fundamental theorem of calculus right now, because this goes in with, this is what allows us to find the exact area under any curve on a function. Okay, and we're going to do part 2 first. And basically it says this is when we're given the equation and we don't have the graph and we don't have bits and pieces of information, we just know what the function is. So if we're given the equation and we want to find the area under the curve, we can do this. This is what lets us find the exact area of the curve. Basically, the fundamental theorem of calculus says, if I want to evaluate the integral from a to b of f of x dx, that is equal to, and I'll do big F, evaluated at b, minus big A big F evaluated at A. And basically what that means, this big F is the antiderivative. So it tells me if I want to find the integral from A to B of f of x dx, I find the antiderivative, evaluate that antiderivative at the upper limit minus the evaluating the antiderivative at the lower bound. And that will give us the exact area under the curve. That's fundamental theorem of calculus part 2. And that's usually abbreviated FTC, fundamental theorem of calculus. You know we like our abbreviation. All right. And that is the definition of a definite interval. So definite intervals, you get a number answer. We're going to get a numerical answer, an area answer. So let's try some. I want to find the interval from 1 to 3 of 2x squared minus 12x plus 13. Now, the first time I'm doing this, I'm going to show every step. I'm going to show more steps than I expect you to show in your work, because I want you to see how it works, how this fundamental theorem of calculus works. And then the second example, I'll show you the shortcut of what the minimum amount I expect to see on your work. Okay, but I am going to show a lot more work than you'll probably ever write again on these problems. Okay. Okay. So step 1, we need to figure out what the antiderivative of this function is. So I'm just going to write it over here as big f of x. I just want to figure out the basic antiderivative in terms of x. So what would be our antiderivative for this equation? 2x cubed over what? 3 minus the 12x over 12x to what power? 2 over 2 plus 13x plus, see, so let me simplify that. So our antiderivative is 2/3 x cubed minus 6x squared plus 13x plus c. You okay with that? And so our upper bound was 3. So that meant I now need to evaluate this antiderivative at our upper bound. That means I'm going to replace every x with 3. All right, so let's try each number. 3 cubed is 27. 27 divided by 3 is 9. 9 times 2 is 18. That's 9. What's 9 times 6? 54. So minus that 54. 3 times 13 plus 39 plus c. And now I got to figure out 18 minus 54 plus 39.
Adding
3. So I get the antiderivative evaluated at 3 is 3 plus c.
Is this a problem?
I don't know.
Is that a coincidence?
Okay, now I'm going to try my antiderivative at 1. So I'm going to replace every x in my antiderivative equation with 1. All right, let's see. That gives us 2/3 minus 6 plus 13 plus 3. 23 over 3 plus 3. Okay. Is that okay? So our formula, remember, in order to find the this, we needed to figure out the antiderivative at 3 minus the antiderivative at 1. So we know our antiderivative at 3 is 3 plus c. And I need to subtract what I found my antiderivative at 1 to be, which is 2/3 over 3 plus c. Okay. Now to work this out, that gives us 3 plus c, distribute my negative, that's negative 2/3, or 23 over 3 minus c. What happened?
C's cancel.
The c's cancel out. Now that is a pattern. C's will always cancel out. Okay? Because I said you'll get a number, and we'll get a numerical answer. So 3, I can rewrite that as 9 over 3 minus 23 threes equals. So the area under this curve from 1 to 3 of 2x squared minus 12x plus 13 is equal to negative 14/3. So I have a little bit more under the x-axis than above. Negative 14/3.
And then, right.
Okay. Now that's a lot to write on every problem, right? So we're going to simplify our notations a little bit.
It's still not working.
No, it's not. By nothing, it's not the word to write. So we actually come up with an easier way of writing that. First key is we notice that the C's cancel out. So we're just not going to write C's because they always cancel out. So we don't have to write them anymore. Okay, so only on definite intervals do you not have to write C. Well, here it's okay to forget it. All right, so x to the 5th minus 4x cubed plus 4x plus 4 dx. Okay, so I'm going to find the integral, the definite integral from -1 to 0 of x to the 5th minus 4x cubed plus 4x plus 4 dx. All right, step 1 is the same. Find the antiderivative.
X to the 6th of the 4th minus 3x cubed,
Where'd you get -3?
because
Wait, that's important. I mean, minus x of
x to the
So it's just going to come x to the 4th because this will be over 4, which cancels out with that 4. Okay, next term. Two x squared. Because that becomes 4x squared over 2, and the 4 over 2 simplify down to 2, plus 4x. And I can forget about the c. And then this is how we tell the reader we're going to evaluate this from our upper limit to our lower limit, from -1 to 0. We say evaluate it from -1 to 0. Okay, so that gives us that whole big F of 0 minus big F of -1.
Where's the other bracket?
You don't have to do it. It just does at the end like that. Sometimes in some textbooks, you will also see it written like this, a straight line. You'll also see it like this, evaluate it from -1 to 0. Either way, whichever notation you feel most comfortable with, I'm good with. Okay? I kind of switch back and forth. So that's what it means. So once you get that, you're ready for the next step. And so basically, I'm going to take my upper limit and substitute it in. So I need to see this direct substitution in without doing any simplifying. So I'm going to replace every x with 0. I know you could probably figure this out in your head, but I still want to see that. And I'm going to put that in big parentheses because that's my f of 0, my f of my upper limit. Okay, I know. I want to see the direct substitution. I know you can figure it out pretty quickly in your head. That was what you want to do. I still want to see that direct substitution. And then I want to see minus. And then I want you to substitute in the lower limit. So that's going to be -1 to 6 of 6 minus -1 to the 4th plus 2 to the -1 squared plus 4 to the -1. And put that in big parentheses. Now, Next step is just depending on you, on how much you want to show. I could just punch this straight in my calculator and figure out what that is. So what is that going to be equal to? 0. Minus, now I can just do this straight into my calculator and figure out what's inside the parentheses, simplifies down. So -1 to the 6 becomes 1, so that's 1/6. I don't have a calculator, so I'm going to do it in my head. Minus 1, that becomes a positive, so that's +2. Minus 4, well, that becomes a +1 minus 4, which is -3. So I have 1/6 minus 3, which is 18/6. Gives us a -17/6.
With the brace supposed to be at the end.
Huh?
Beginning,
What brace?
on the beginning of the road.
That's a print.
Yeah, those are my parentheses.
Okay, looking for-
Yeah. You know how this sometimes doesn't write well with me. No, that's the parentheses. And so, but don't forget I have this negative here. So I got negative of a -17, so that gives me 17/6 is my correct answer. My area is positive this time. And so that's all the work you have to show. So it's a little bit shorter.
Now we can.
Let's do one more. Two more. I want to do 2 more. How about, let's figure out the integral from -3 to -1 of 4 over x dx. So what's my first step? Find the antiderivative. And I think for me to help me find this antiderivative, I'm going to take that constant out. So what is my antiderivative? So 4 times the natural log of the absolute value of x is my antiderivative. And I'm going to evaluate this from -3 to -1. Okay, plug in the upper limit first. So 4 natural log of the absolute value of -1 minus, plug in the lower limit in my second set of parentheses. And that's going to be 4 natural log of the absolute value of -3. Well, what is the absolute value of -1? 1, so that becomes 4, the natural log of 1, minus 4, the natural log of 3. So the absolute values are very, very important that you do the derivative from this. If you don't, you try punching in natural log of -1, you calculate, you get undefined. So you gotta make sure you remember those absolute values. Now, here's a good identity that you should know. What is the natural log of 1 equal to? This is another one we just have to know. 0. So that becomes 4 times 0, which is just 0. Minus 4, the natural log of 3. So my answer is -4, the natural log of 3 is the area under this curve. Okay, the last type is a piecewise function. She kind of ended it on here, and I don't know if you paused before she threw up, because she kind of threw up the answer in the middle of her telling you pause and work it. So you might not have saw that, you might not have had time to try it. I hope you did. But I want to try a piecewise function. So this is our last type. The integral from 0 to 3 of f of x dx. If f of x is defined by the piecewise function x over 2 minus 1 when x is less than or equal to 2, and x squared minus 6x plus 8 if x is greater than 2. Okay. So to do piecewise functions, the first thing you have to look at is look at the integral in which we're trying to find. We're trying to find 0 to 3. And then see if that's all in one piece or if it's broken up between the different pieces of our piecewise function. In this case, is it in one piece or broken up? It's broken up because 0 to 3 counts. We say we use this equation where we're looking at all numbers less than 2, but we use this equation when we're looking at all numbers greater than 2. So we have to break it up. So Since that, we have to switch equations to evaluate the integral from 0 to 3 of f of x dx. I have to use those properties and say that's equal to the integral from 0 to 2. And I'm getting the 2 because that's where my pieces of my piecewise function is broken up at. And then when I've been looking at from 0 to 2, that's less than 2, so I'm looking at this top equation. Plus the integral from 2 to 3. So I'm using that properties that we talked about earlier of our f of x function, but when I'm going from 2 to 3, I'm looking at this bottom equation. So that's going to be x squared minus 6x plus 8. So we have to break it up based on how our piecewise function is defined.
Can you get 0?
Yes, absolutely. Okay, so that's my setup. And so now I have to do two antiderivatives. I have to find the antiderivative of this first equation. So what's the antiderivative of x over 2 minus 1? Time you do it. Work it down.
X squared over 4, x squared over 4.
X squared over 4 minus
Okay.
x, and I'm evaluating that side from 0 to 2. Then I'm going to add the antiderivative of this other side. So what would it be?
X cubed over 3.
X cubed over 3 minus 3x squared plus 8x. Now this one, I'm evaluating from 2 to 3. So that would be the setup I would do for this piecewise function. And so now I got to do my upper limit, upper bound for this first piece. So direct substituting in 2 squared over 4 minus 2 minus substituting in my lower bound, 0 squared over 4 minus 0. Always like the 0 ones. They come out nicely. Plus, now I got to do direct substitution in of my upper bound for the blue equation. So that's 3 cubed over 3 minus 3 times 3 squared plus 8 times 3 minus plugging in the 2, the lower bound, 2 cubed over 3 minus 3 times 2 squared plus 8 times 2. What was another set of parentheses there? Okay. All right. 2 squared is 4. 4 over 4 is 1. 1 minus -2 is -1. What does this parentheses simplify down to? 0. So that's easy. All right. How about this one? (27) over 3 is 9. 9 times that is -27 plus 24. Okay, so that one's 6. Minus, that's 8/3. Minus 4 times 3, which is 12. 8 times 2, which is 16. So that's +4. So that's going to be 12/3 and 8/3, which is 20/3. You will get used to fractions, hopefully, if not yet. Okay, so that gives us 5 minus 20/3, which is 15/3 minus 20/3, which is -5/3. And that would be our area of that piece. Now you can do the rest of the problems. So this is our fundamental theorem of calculus part 2, or how to evaluate definite intervals.
Yes, sir.